Okay, so my topic of this lecture is neutrino detectors. Okay, I think I will spend 5 minutes just to tell you at the end when you find that I could not satisfy you. One of the main reason is, let's say the neutrino detector. Actually, last year we had an ICFA school at Mumbai. Many of you are maybe there. There the 2 weeks was spent just for this detector concept. And usually when I give a lectures in this graduate course, it is about the 50 hours lectures where I cover the neutrino, cover the different conventional detectors, basic principle, not individual detectors. And now I was supposed to give you the 3-hour lectures and I requested to the extended 4 hours to cover all this. So what should I cover? So now actually earlier talk you heard little bit of neutrino physics, it will continue. Last many years, what are the neutrino detectors I came across? If I just put the list of them, starting from this, okay, I did not even put this earlier 1950s. So 1965 onwards, these are the experiment, discovery, neutrino discovery and other, this is helicity, parity violation, all those experiments, excluding those. These are the experiment started from the 1965. There is something, actually this is not this properly ordered. And then there is another experiment. And this is not the exhaustive list of the neutrino experiments. And now what should I talk on this? If I try to slow up this one slide of each of the experiment, even I could not cover. Okay? So that's this my job. They give me the job. And only thing, one thing, they give me the fee and that what I want to tell, I will tell you. So based on these configurations, so I will talk, and as I said this already, this is the Nobel winning lecture also missing, so many more experiment was missing. So in this talk, only one thing I just okay, this is also not my starting of the lectures. These are two experiments I just put, LSND and Carmen. These are two experiments was done when I was a graduate student in 1990s and that time. And the two experiment was exactly same experiment. This is this as the same thing starting with the pion decay to the muon decay to the electron, that the neutrino happening, neutrino produce, and the neutrino has any oscillation or not. And this experiment sees this some anomalous result, LSND. Carmen did not see any anomalous result. But all over the world rejected this Carmen result except this LSND. And I asked many experimentalists, many phenomenologists, many so-called physicists, there is no clear-cut answer why this experiment was forgotten and why this LSND experiment was used. And to prove or disprove the LSND experiment, there is a initially the mini-mono experiment, then now the micro-mono experiment to say that what is the anomaly they have seen to see or not. Okay, this is just only one thing I am saying, that somehow all over the world, if something anomaly is happening, people jump on this. And one thing is true, that neutrino when it comes from the anomaly. All these neutrino oscillation, neutrino event, all these are coming from the anomaly. That's why maybe this, in the neutrino experiment, this may be the right approach. When you see the anomalous signals, you are expecting something will happen. Okay, so based on, after that, I just try to tell, this is the summary of this my preschool lectures. Actually, it was 3 lectures, but it was even more than 5 hours. So what is the summary? I think there I give the 6 bullet point. These all the high energy physics detectors are built to detect so-called stable particles. I say that this is the so-called stable particles, basically whose lifetime is greater than 1 meters, such that particle can go through the detector, interact with the medium, and you can see it. And the detectors I categorize in the 5 different groups. And the best approach to utilize the electronic interaction between particle and medium to design the HEP experiment. And that's the things, but except these weak interactions, neutrino and the neutral hadrons. But this is the detector design was neutrino started with the weak interaction, And neutral hadron starts with the strong interactions, but when you detect this, then we use the principle of the electromagnetic interactions. And signal mainly from the ionization energy of the charged particle as well as the Cherenkov and transition radiation act, not from the trajectory of the neutral particle or from any interactions. So these are the very conceptual point. Of course, there is some exceptions will be there, but this is the standard convention we use, standard technique we use. And all the signal in particle detectors are due to the induction of the moving charge. I will again hammer your head on this point. When charge arrive in the electrode, signal is over. Means signal is not propagated to your electronic circuit. And there is a conventionally two kind of detectors we use. One for the energy measurement calorimeter, another called this tracking device, where the magnetic field measure the momentum from the radius of curvature. We measure the momentum of the particle, and calorimeters. This is the dominant effect of the energy resolution goes A by square root of A is a constant square root of P, and tracking resolution is goes proportional to the P. So for very, very high energy, calorimeter is better, but low energy tracking device might be better. An experiment of rare events, particularly Neutrino experiment, has to be done in the underground, and this is not only remove the muon signals, but also the background from the muon induced cosmogenic backgrounds. So this is not only for this muon event, muon we can veto, but this muon induced cosmogenic in backgrounds, that's the large background gives this neutrino or the dark matter experiments. Okay, so now after that, let's say now this talk and earlier talk also, first my disclaimer is that most of the content are not my own work, and almost all plots, data, many texts are taken from others' presentation, other works. Particularly today evening when I'll talk about this little bit of Kamiokande detectors. Actually, incidentally, this was my plan. Let's say I'll come back to this one. So in my lectures, my primary emphasis on these 4 lectures to give the examples of development of the detector element. So we have some physics goal. Let for example something neutrino has to detect. How to detect the neutrino, how this is materialized or design the instrument for that. This is, as I said, development of the detector element to achieve the well-defined physics goal. And we have the detector element, but the detectors, when you say that I see this neutrino energy, let's say 10 MeV, how do you assure that what you observed is the 10 MeV? This is the one of the integral part of the system, the detectors. I will talk about the little bit of calibration systems, and it will mainly focused on these super Kamiokande detectors to talk about this. But I will not talk about other important ingredient of these neutrino detectors, basically engineering. As a big experiment, that is like physicist, theorist, our experimentalist, we experimental physicist, civil engineer, mechanical engineer, electrical engineer, electronics, computer engineer, chemical engineering. These are the much more important role, particularly when you go for the neutrino detectors. Chemical engineering is a big role plays there, but I may touch upon a little bit, but I will almost not talking anything on this. And this plan of this, my 4 lectures will be initially I will give the introduction. Already you have a little idea, what is the source, how the neutrino interacts. So basically, this gives me the guideline that what kind of energy we want to see in our instrument and how we can design the instrument for that. So the first lectures will be today's, the morning lectures will mainly follows these things. Basically general purpose, like the general things. But in my preschool, I talked about this general detector concept, which was this in general high energy physics detectors, not for the neutrino or all other experiment. But here I will mainly focus on these dedicated neutrino experiments. But what order should I follow? I could not, I juggled here and there, so this may be a little bit haphazard way, I will show all these things. And my second lectures, I will go through a journey to this Kamiokande, to the hyper Kamiokande. Basically, I will just go through that what was the design of the Kamiokande and what was required to look for the solar neutrino experiment. And Kamiokande experiment cannot just directly use this solar neutrino experiment. It is completely looks like a new design of the electronics. Many things was done. And then this is the and the super communicator came. And there I will spend a substantial time on this calibration of the super communicator detectors, basically starting from this few MeV to the GeV energy. How we are sure that what you observe, that is the really that energy, incident particle or incident neutrino was that energy. I will cover that. And third lecture, I will try to cover these two experiments, Juno and the Dune experiment. And particularly these three experiments, I am just trying to tell this is the one of the pioneer experiment. For many years it will come, and in the coming years these two are the most important experiment for this neutrino physics. And then in the third day, fourth lectures, I will try to cover some other detector, let's say neutrino double beta decay and some other thing, general detectors. Okay, so now I go back to the summary of this my neutrino experiments. So as you already know, neutrino are oscillating. This is the oscillation between the second and third generation, third and fourth generation, and first and second generation. And these generation parameters of the generation is mainly coming from the atmospheric neutrino or long baseline neutrino experiment. And for this was the θ13 and others, it is coming from the not exact short, means kilometer range baseline experiment and the neutrino beam. And this is this first and second generation, the oscillation is started with the solar neutrino and Cumland, another experiment we have. Okay. And delta CP violation measurement of the asymmetry of the mu oscillations, I will not talk at all, I am just mentioning it. And this in the oscillation we did not put, we just in the previous lecture I was mentioning this Majorana phases. I will not talk about anything, so this is not appeared in the neutrino oscillations. So these also I will not talk almost at all about this. And if I go to the time evolution of our understanding of these neutrino oscillation parameters, so basically we are talking about the θ13, θ12 and θ23 and delta 12 or 21 and delta M32 square. This is the modulus. Till now we do not know what is the sign of this, and these are the different experiment what previously I showed that gives these parameters. And if you go to this year wise, how we know these parameters, this is what is the uncertainty. As time goes on, this uncertainty is reducing. Particularly this is this Cumland. This gives you this sin θ12 or the delta M2 measurement is much more precise. Similarly, this is this 2012, all these detectors, they pin down this value of this sin θ13, and then T2K also measure this little bit of phase, and this other measurement gradually with this time we are having the better and better understanding of this measurement. Okay, so now what are the different sources we used to study all this? And if you have to see, okay, this is also random orders. This is atmospheric neutrino, cosmic interactions in the upper atmosphere produce pi plus mu plus, which decay generate this nu mu and nu e, and this flux is roughly 10 to the power 3 meters per second. And this is the typical example, is the pion decay to the muon neutrino, muon decay to the electron and 2 neutrino. That's the way you see these interactions. Okay. And then of course one of the major source of the neutrino is the sun. This is the sun, it comes roughly 10 to the power 14 neutrino per meter square per second. And then the man-made neutrino sources, nuclear powers. These nuclear powers where produce the neutrinos. And then also we have the neutrino beam, which produce the neutrino from one. This is again pion decay to the muon, and that the neutrino will see. This is the neutrino beam. And actually recently there is a new experiment also started for this neutrino experiment to look for this TeV energy neutrino. This is actually LHC experiment. This is the LHC collider point, and this is my beam line. And in the interaction many particles are produced, and when it go in along these directions, here we put the neutrino detectors, and these detectors can detect the neutrino. This energy of the neutrino may be the TeV neutrino. Okay, so these are this last few years this experiment come up, and then this is the Geo neutrino. This is the earth crust where we have this potassium, uranium, thorium, and this decay gives you the neutrino, and that's also the neutrino you can measure. Supernova neutrino, actually this is, I think I will not talk at all, but this supernova neutrino exists, and this energy of the neutrino, okay, oh, this is the supernova neutrino. It is the once in a lifetime we see. I will only show one slide about this 1987 supernova neutrino in this Kamiokande experiment. And the Big Bang neutrino, cosmic neutrino, this energy was very small, and that I will not talk much about. So these are the different sources of the neutrino we have or we made it, and using this neutrino, we have to make in our instrument by which the neutrino interacts and produce this neutrino interaction detection mainly through the charge current interactions. So it will produce the electron and muon, and that we have to detect. And then this is the charge current interactions. I think there is a much more dedicated talk will be the cross sections of this neutrino. I will not go through at all. Only just trying to say that with this energy, different kind of neutrino interactions, other cross sections are the different. And this is the mainly this neutrino cross sections for this atmospheric neutrino. And this is the energy range what is used for the solar neutrino. And this is the reactor neutrino energy ranges. Okay. And then when you go for this atmospheric neutrino, and there are these neutrino interactions, this is the charge current interaction. So this is this nu mu gives you the muon, but there is also quasi-elastic resonance and deeply elastic scattering, and as the energy, how it goes of the different cross sections. But after a certain 10 GeV kind of things, it is almost flat cross section per E. That is the way, or you can say the cross section is go proportional to the energy of this electron energy and neutrino energy. This cross section goes like this way. And these are the different few experiments which energy range they took. T2K nova, long baseline neutrino experiment, mainly this now the Dune experiment, and this was the experiment in the Grand Sasso experiment where actually this nu mu to nu tau oscillation was discovered, and that this beam energy is roughly a few tens of GeV. Okay. So these, again I am repeating, I have these neutrinos, these are the neutrino source. Depending on the neutrino energy, it will produce this electron or muon, and this is an electron or muon, and then along with the electron or muon something else also will produce. And now we have to design an instrument by which we can measure this energy and direction. When I say measure means identifying the particles with these 4 vectors. That means I know the direction of the momentum, and from that I will interpret these neutrino properties. So now let's say go back to my standard detector concept. I think this slide I showed in this preschool, again I am repeating. So interactions of the charged particles in the medium, as I mentioned this, in general all the experiments were to use where the charged particles deposit the energy, and that energy measures, and that way try to interpret, go back to this what is the initial particles. So when the charged particle pass through the medium, this is the kind of an pictures you can say a charged particle pass through, and in the charged particle pass through in a medium means there is some our atoms are there, where the nucleus and the electrons. And the charged particle when it pass through, this is generally 4 different kind of interaction it can happen. This ionized atom in the traversing medium, when it particle go through, this electron, it may be just electron may be a knockout, this ionization, that is the electron a knockout, or electron go for this state to another upper state in the free available state, and when it go to the excited, and then maybe electron come back to the de-excitation, this gives you the photon. So these are the first interactions. This is either excited or ionizes. And but on the other end, when the nucleus go to the very close to the nucleus or maybe the electron also, this is the electron nucleus interaction. That means there is an electrostatic force. So it means this electrostatic force, this neutron either accelerated or retarded. So you know that any charged particle when it accelerated, it emits a synchrotron drops, photons. So here is also this, when the particle see this, it emits photons, and it's the defined nomenclatures is called the Bremsstrahlung photons. Bremsstrahlung photons. So usually synchrotron means we say that electron, a beam moving in a circular path in the magnetic field, that the synchrotron, and when the same radiation, principle is same, but when the radiation occurs in presence of the ionization, charged ionizations, charged particle, that's called the Bremsstrahlung, and it goes, properties is proportional to this 1 by m square mass of the particles. That's why this is the dominated mainly for the electron. The charged particle electron mass is 511 keV, next one at 106. So that means that if you see this muon effect is roughly 40,000 factor is smaller than this electron. So these properties mainly we see for the electrons. And other two properties also we see when the particle goes in the medium, in case the velocity is larger than the velocity of light in the medium, resulting in electromagnetic shock wave. I will come to one slide on this. It's called the Cherenkov radiation, and this is the principle very elaborately used in this neutrino experiment. And only another thing, I just to complete this, I just put is the transition radiations. When the particle moves in between the two mediums of different dielectric constant, and there also when this particle move, particle electric field, when it moves transit from one medium to other medium, the electric field is changed, and that's in this quantum mechanical, if you electrodynamically, if you try to interpret, it can go through a X-ray photons, and this is the X-ray, this is the some keV energy range, and it's called the transition radiations, and this Cherenkov radiation is this mainly the UV range. And just one point I said, these three things, we use it, Bremsstrahlung photon, Cherenkov radiation and transition radiations. And if you want to go for this more on mathematics, what is this properties of this, you will not find anywhere any high energy particle physics group all these derivations. But all are given very elaborately, explicitly in Jackson's classical electrodynamics book. As I said, if you want to know more on this, you just follow the classical electrodynamics books in Jackson, what you read in your BSc or MSc level. That book has all these things. In our case, we just use these expressions. We do not derive the expression, go through these mathematical derivations. Then, this is this when the particle go to the medium, when the ionization energy loss happened, and it was this ionization energy loss first is derived by this Bethe. Again, this is same Hens Bethe. He derived these expressions, and his expression is something like this. So basically, energy loss goes incident particle charge square by incident particle beta. Beta is velocity by c, beta square, times some log of this is the gamma square. So that means when the momentum is very small, the energy loss will be very large. So here is this pictures. If the particle momentum, what is the energy loss we will see for the particle momentum. For the different particles, momentum beta can be different. So this is this pion, electron, kaon, proton, deuterium alpha. That is the way energy loss will go. And then with this, when the energy is increasing, it will go logarithmically log of gamma square. So after a certain time, here is the minimum, then it will go up. Minimum occurs roughly at beta gamma factors is 3 or 4, is in that range. And this is the some other correction was taken because of this particle when it go, it will polarize this medium. So those kind of effect, because of that reason, there is some correction factors was there. Basically, this polarization means is shielding the incident particle charge. So this correction term was used. Now, if we know a particle is going to a medium and it loses the energy depending on this formula. So if the incident particle has a certain energy, it can go only certain distance. This example actually when I go to the school level to teach it, I say that if you have a marble, throw in the floor, what is the initial momentum of the marble? You throw, it will go more distance. So this is exactly the same analogy. If the incident particle energy is more, it can traverse a longer distance. And these are the properties we used to measure the total energy of the particle sometimes. How much distance is traversed? Depends on this, what is the incident initial energy, and this is it say that again slightly different way. I say that particle here I put this beta gamma factors, And if we convert in the momentum of this muon, pion and proton, this is the momentum range, and how much range it will traverse compared to the different mediums. And in the book, when people talk about the dx or this range, everything, always you derive using this expression 1 by rho. So in the nuclear physics concept, they do not say this 1 by rho, but they implicitly it is 1 by rho. Why I wrote here 1 by rho dEdx, actually that is the dEdx plot is here. Here 1 by rho factors you have to include. So that's this convention people follow. Okay. So like that in the high energy physics we say that we do not put C and H all put as a 1. So here is also nuclear physics and a low energy experiment. Usually when you say that dEdx, that means 1 by rho factor implicitly there. And why this 1 by rho factor implicitly there? If we use the 1 by rho factor for the defined mediums, this path length is almost independent of that. And this is exactly the same if we modified rho into Z by A. Okay, so that's the way. So basically these are the, depending on this particle momentum, you have a range. If you do the range, from that you can get the particle momentum, charge particle momentum. And so based on that, conventional tracking detectors was used like this way. When a charged particle passes through, it loses some energy and it gives the electron excitation that gives the electron and ion. And if we have this anode wires, this is a very conventional what the Geigel-Müller counters. This electron will move close to these anode wires with the electric field, and close to the anode wires, electric field configuration is in this configuration is 1 by R. So when you close to the anode wires, this field will be very large. So this electron will have a sufficient energy to knock out an electron from the atom. So that's the way, something like this. One electron comes, when it comes close to these anode wires, the number of electron multiplication will go very, very large. So that means at the end, at the anode wires where the electron reach, there the large number of electrons are coming. Okay. So this again I am repeating, I use this word when electron is reaching, but signal is coming because of the motion of the electrons in this electric field, these regions. And I think these I explained in this preschool. I will not go just to complete this, I show it. And then this is the similar concept we use for these liquid argon detectors. And that is used, I will elaborate on the, I think, third lecture, I will spend much more time on this. So this concept is this. Here in this liquid argon, when the charged particle pass through, here the picture is something like the neutrino coming, it produces the two particle trajectory, charged particle are produced, and charged particle when it moves along this path, charged particle lose the energy. In this case, it loses the free electrons, and also I say that ion will excite it, and when it de-excited, it emits the photons. So simultaneously it gives this charged particle and this my photons, and photons is immediately collected in this surface area with this some photo device, that I will come later. Photo device, in this photo device, we know that when the charged particle is passed through and that electron, it drifted slowly to this my plane, anode plane, and anode plane there is a different, let's frame this example is the three different planes where the anode wires in these three angles roughly 60 degrees with respect to each other. And in this anode wires, when you see the signals, the induced signals in the three anode wires will be something like this. So this picture is this, induction is, electron is coming to the anode wires. When electron is come to the anode wires, the electrons, this is the negative charge, when it come to the anode wires, it gives this negative electric field. So the induced signal will be the negative, and when it crosses it, again it go off. And of course, this is not that exactly these electrons moving. Our electronics readout, that shear circuit also come into the play there. So the signal shape will be like this. And the last anode where the electron will just collect, and there the signal is only unidirectional signals. And this is the pole zero effect, this is the electronics, completely different part of the electronics. So the motion of the electronics should not give the signal anything here. So the time information when the ionization electron arrives, that gives the distance from these wires. And geometry information, so this is this, in this three plane, we get this geometry, the transverse position we get. and how much signal we collect, that gives the total ionization energy deposit of this trajectory of the particle that we will use to identify the particles. Now, also we have to detect sometimes the photons, and this slide I did not show in the preschool because that was the different, but here you explicitly need this. So this is the interaction of the photons. Usually conventionally you read this photoelectric effect, Compton scattering and electron-positron production, that we say that electron pair production it happens. These are the three processes you know. But one more process, I think before all this you learn, this is the coherent scattering, where the scattering goes 1 by lambda to the power 4. That's why I think everybody learned why the sky is blue, but in Bombay nowadays we do not see the blue sky because of this pollution. Okay, so you know that why this sky is blue, this explanation why the morning sunshine is more reddish, so that the explanation is coming from this scattering. And this also in our experiment to use, we have to take care of it, but this is not as a useful device for us, it gives us the problem to us. Another thing also, this is the photonuclear effect. These also we will not talk about. These two factors, this is the coherent scattering, and this coherent scattering I will talk a little more on this. Where it is. So this is the inherent problem in the propagation of the lights, and this is the problem in high energy physics, but tool in the nuclear physics. But these three processes, when you talk all these processes, cross sections, how they depend on this momentum, depending on the particles and this energy. So let's, for example, in our case, in nuclear physics experiment, we will use this, sometimes we will the photons. What are the photons? Energy of this about an MeV range photons. As he showed, this is the positron annihilation, it gives the 511 keV photons, or when this neutron and nucleus, the neutron absorb in the nucleus, go to the excited state, gives the photon, that is the MeV range of photons. So roughly something MeV range of photons, and in the MeV range of photons, when this is the, let's for example, you have the scintillators we will use, where mainly the carbon is the one component, where in this case, the dominant effect is either this is this, in this case, the dominant effect is this only this Compton scattering. And if you go the high Z material, there is a little bit of my photoelectric effect, and also the Compton scattering process is there. So we will use, this is the Compton scattering process, mainly the Compton scattering process to convert this photon to get the energy. So few things I just mentioned here. This gamma, what we will see, we will not see the gamma directly. Either the Compton or photoelectric, it converts to the electrons, and when electron or positron, it goes to this medium, it loses the ionization energy loss. That gives you this, my ionization, that gives the signal, and ionization energy loss gives you the charge or visible photons. And this produced gamma, what is the gamma is produced, that's why I say that this is gamma is about an MeV order gamma. These are very much different than these visible photons what you observe in EV. So this is this interaction, this gamma what they produce, this is the MeV order, and what we see in the gamma we call gamma, this is the visible photon, this energy is 2 to 3 electron volt. So these are the completely different electromagnetic waves. And how do you detect neutron, a neutral particle? It captures in the nucleus. This is the neutron comes, if it is the hydrogen, it gives the deuterium, it produces hydrogens. Sorry, this is the 1s2 it created, or in go to the gadolinium, it gives this excited state, de-excite gives you the 8 MeV photon, few photons of the energy of MeV. So that MeV photon, again it from this capture of the nucleus, in the nucleus, that goes the binding energy is the gamma, and when it produces the gamma, it comes to again the same chain. Okay. So these are the way we detect this gamma and neutron in our neutrino physics experiment, and these are the pictures we will repeat again and again many times. Antineutrino, he already explained this antineutrino, this first signal is the positron, annihilations gives you the signals, but immediately after a few microsecond times, we see this 2 photon signal that you will try to reduce the background, and also to increase the strength, we use the gadolinium, and that is the number of photon, energy of the photon is more, so the signal is much better. Okay. So these are the way we detect this gamma and neutron in neutrino experiment. And then this I say that gamma gives you this my charged particle of the visible photons. So visible photon means you have to use some scintillator materials where this valence band and conduction band, the gap between them or this what the photon will emit, that should be about an visible energy range. And this visible energy range, if we have the device where it go to the within the visible energy range, we can directly use. But most of the physics process, what we do, we put some impurity such that in between there is a sum of this state are created, and when the transition occurs within that state, that gives you the scintillation photons. Scintillation means energy of the photons is 2 to 3 electron volt on a visible range which we detect. Okay, so the principle of this ionizing particle produce free electrons, elevate the electron to the ground, from the ground state to the excited state, and excited state decay to emits the light. Now the band structures, that's the way we design our detector. But in the detectors, the requirement, this is very stringent requirement if you have to have this better physics, convert the charged particle kinetic into detectable light of high scintillation efficiency. That means it should not happen that if this 1 MeV photon gives only 1 MeV photon, 1 MeV photons correspondingly gives you only 1 electron, 1 visible photons. Then the 1 visible photon is the, you say the Poisson's distribution on the average, you have the 1 visible photons, it may have this large probability of the 0 photons, so inefficiency. And also you cannot have this energy measurement with this energy measurement very large. And scintillation output should be linear to the kinetic energy. And that is not the true case for most of the times, but we try to make it as linear as possible. Transparent to the wavelength is own emission. That means this what the photon emits, it should not absorb within that medium itself, it should come out. And short decay time, that means this state should not be a long lifetime. Then we do not know when the incident particle come and when it decays. And the refracting index near to the roughly 1.5. To permit this coupling to the phototransducer, basically this is the scintillator. So when you collect with this converter, this usually we call this photomultiplier tubes. You know that if the refracting index does not match, there is a reflections. So that's the thing, it has to be like refracting index and good optical properties. The main thing is that to make a detector at the large scale, this is the one pictures I took from the CMS experiment where roughly 22 centimeters long crystal was made, and this is actually one of the R&D in 1980s, 90s, and this is my career, starting of my career in this high energy physics, where we try to see what is the radiation effect of these crystals. These detectors, starting from the scratch, that we have to lead tungsten crystals, which can be useful for the CMS experiment, or this not the CMS. That time this concept was that choose a material for future collider experiment. CMS was not in the picture even at that time. These detectors, from this concept to making these detectors, it took 20 years. Just to starting concept that we have a lead tungsten crystals can be property and get this crystal, it took 20 years. So this is each of these detectors take a lots of R&D, and scintillator detectors mainly inorganic, organic, and nuclear physics mainly we use the organic scintillators either liquid or plastic form, or in the noble gases, as I said, the liquid argon or liquid xenon gives you the scintillator light. And scintillators you are familiar. First experiment, if you say that what in a high energy experiment, you remember that the Rutherford experiment. You know, the Rutherford alpha particle were detected with the zinc sulfide screen. There the scintillation on alpha heat, it produces the scintillation on the zinc sulfide screen, that the scintillator lights. And as I say, scintillator lights, these are the two things I forgot. Usually in Bombay, when I used to take this class, I used to show some samples of this instrument, and photomultiplier I could not bring. I bring some of this scintillator, plastic scintillator. Later on you can see this is a different kind of scintillators, and this is some kind of fibers which you use. And in the next 2 or 3 days, all the experiment I will talk, I will just show those are the things, properties of this. Okay, and then actually photomultiplier tube I could not carry in the plane, because otherwise I would have shown, and usually in Bombay I used to show an example of this photomultiplier with all this. So photomultiplier, this is the device which was developed in 1940s, And this is the only device in high energy physics we use where we do not know exactly what it is. I'll just come to this point. This is a kind of a history. Okay, this device is conventionally, this is the three parts. One is this is the glass scintillators you see. This is the convention, what is the photocathode? On the glass, you have a photocathode materials where the photon incident, it converted, gives you the photoelectron. This photon is the visible energy range photons, 2 to 3 electron volt. This is this when I call photoelectron, and this electron, this is called the diode. This electron, and here you have an external electric field, roughly a few hundred electron volt. And electron will oscillate it here. When electron will hit on this, electron on this surface, this is mainly, this is the alkaline material, this potassium, bismuth, those are the materials. And here means basically with the copper beryllium kind of material, where electrons, it produces many more electrons, multiplication occurs. When it produces, let's say 1 electron to the 4 electrons, now with respect to this diode is higher potential. So this electron will oscillate it to this here, and that's the way electron will multiply, and at the end it comes to the anode. Okay, that is the way it goes. These pictures. Okay, now what I said that this is the only device we do not know the ingredient. We do not know what is the thickness of the photocathode material, what is the coating, this copper beryllium we give, what is the coat, what is the thickness of that. This was developed in 1938 or 40s. And that time, this was patented. So in the official document, you do not have these numbers. This is what is the thickness of the photocathode, what is the thickness of this copper beryllium. And this is the only two information in high energy physics all my life, what I know. We do not know this exact information because these were patented. And nowadays, we do not patent anything in high energy physics. Okay, and these are the different kind of photomultiplier. This is the variation, and this is the one photomultiplier. Conventional photomultiplier tube is roughly 5 centimeter or 2 inch diameters, and this is the big photomultiplier which is this used Kamyokande. This is the 20 inch diameter like this. And first time when I saw in the one of the open day in KEK, I could not believe this is the photomultiplier. The 20 inch, this is the size of this photomultiplier. Okay, so this is the different sizes of this photomultipliers. And then in the scintillators, we use mainly plastic scintillators where we'll wrap up. This is one of the example of the scintillators. These scintillators we cover on all the side, and light will reflect it, and one side we collected the signals. Or the liquid scintillators, we will have the liquid scintillators, the way we put it, and scintillators with the light produced, we collected the photomultiplier, collect the signals. And in the scintillator, big scintillators, instead of directly to the photomultiplier, many times it is not possible. You have to propagate the signals through the fibers. So these are the one of the fibers. We say that these are the fibers we use to collect the signals. And this fiber principle is that when the light produced here, this light, scintillator light goes along all the directions, and a small fraction will come to the fibers. And fiber scintillator has the property to absorb these photons and emits the large energy photons. Large wavelength photons. Basically, we say the blue light will absorb, green light will emit, and this is this green property you see. This is not this property is coming. This absorb the light from outside, and when it emits, this emits the green light. And then these are the many detectors is used. This is the NOVA experiment. Uses the liquid scintillators where you put the fibers and take the readout. And in this case, T2K experiment, they use the detector where the the scintillator blocks, where they collect, this is the scintillator block, you collect the light in this, all the 3 directions through these fibers. And also liquid scintillator detectors, big scintillators, your photometer collect the signals. Okay. So now I'll a little more detail on the scintillator detector. Let's say conceptually how the scintillator detectors or many scintillator detectors were used in the many past and the futures also. To me, this is the one of the best example where I can explain most of the properties of the scintillator detectors used in the neutrino physics. So this example is for the Borexino experiment. This is the detectors what put roughly 1.5 kilometer under Earth's mountain in Gansaso lab. So this is the steel water tank, 9 meter base radius. So this is a water tank. This radius is 9 meters. And at the 16.9 meter height, this is the height is 16.9 meters, filled with the 1 kiloton ultra pure water. This is the ultra pure water, the blue part what you see. And if something is passed through this area, this is detected by 208 8-inch photomultiplier. These are the photomultipliers here, and these are this photomultiplier which will detect the signals. And the inner detectors within the stainless sheet equipped with, this is the stainless steel equipped with, this is the roughly 2018 photomultipliers. These are the 2018 photomultipliers we have. And photocathode coverage is 34%. 3 inner detector layers are inserted in this 125 micron thick nylon balloon. So this is the 2 nylon balloon we use to separate out these inner scintillators. And this inner vessel and the outer vessel of this radius is, this was the 4.25, this is 5.5. And this was done, this extra things was done. This photomultiplier, one of the base material is potassium. And potassium, this is also the radioactive material. So this, to avoid this potassium, it moves here. This is the balloon, this is the nylon sheet, it prevented it. And this part of the surface, where the inner part they use, this inner part is they put at extra dye material. Buffer consists a solution of the diethyl DMP. Basically, this area, even the scintillation photon produced, it reabsorbs. So it wanted only the scintillation photons what it produced here in this region. And also within these regions, this is the circle inner part. This detectors is called this fiducial volume, where any signals are produced here, they will consider this a signal, others are produced as a noise. So these are the detectors are shielded with the waters, and then this is a buffer layer, and inside the scintillators also we have some of the reasons which is I say that it may come in contamination from the outside. So only the inside something happened, that's in the reason we use, and this is called this fiducial volume. And this is this property used for all the neutrino experiment. What are the detectors? We have a shielding, and then also what is the volume we have? This volume we have, this is the within that whole volume we are not called the fiducial volume. Only we collected the inner part where the scintillator, where we call if something happened there, that is the reason we consider the signal. Just one example, in a Kamiokande, super Kamiokande, you know this 50 kiloton detector, but its fiducial volume is only 22.5 kiloton, less than half of its volume. So I will come in little more detail. So these are the basic concept of the detectors. And another thing keep in your mind, when you make the detector, real world is completely different than the ideal world. These detectors was made with this initially, this photomultiplier was supposed to be 2212. And when it operational started in 2007, 1931 was operational. Either the PMT has some problem or the electronics has some problem, this was not operational. And when it is ended in 2019, only about 11,000 PMT was workable. So that means half of the PMT was dead or not workable. This is the extreme case, but in general, any experiment when you made, this is very much deviating from the ideal world, what is theoretically initially we say that that should be the performance, but so that means this when the number of photomultipliers reduced, our efficiency is reduced, energy resolution is deteriorated. Okay. So these scintillators, little more properties of that scintillators. Here they use the two scintillators. One is the pseudocomin and the fluorescent dye. This is called the wavelength shifters, and this was used mainly pseudocomin. If the emission spectrum is within this range, and this photon will absorb by this PPO, and PPO emission spectrum is this. And photomultiplier quantum efficiency with respect to the wavelength, this was the most efficient, roughly about the 25%. So that's why the PPO was used such that whatever the scintillation photons produced, that is the highest quantum efficiency of this available PMT at that time. And also this is the wavelength, and the Cherenkov wavelength also, this is this in this light, only not on this scintillation photons, the Cherenkov photon also produced, and that the wavelength spectrum is this. And other thing also keep in mind, this detectors I say they are about the 10 meters diameters, and when the photon produced in one side, it go to the photomultiplier tube, within that length it may attenuate. And these are the attenuation at the wavelength, these are the attenuation length of the different wavelength. So our spectrum is roughly 400. So in that region, this attenuation is more than a meters for most of the, mainly this component is this, my pseudochrome in PPO emission here, the attenuation of the few meters. And then this is the kind of an way try to identify the event. For example, again the Borexino experiment, if the some particle muon pass through this here, you call the outer detector muon. Only in this photomultiplier you will see the signals. If it is this muon go through these detectors, we call this B. In these detectors you will see signal, and the inner vertex scintillators. So we will get the signal here, but also signal will go from this point to this point. So how do you know that signal is produced here? If the signal is produced here, photon go in all the directions. So now from this to this direction, how much time it takes, and from to this direction, how much time? From the time measurement, we know that where the scintillation photon happens. And this is the time measurement also, the scintillators and the Cherenkov photons, their property is slightly different. And using this principle at the later on, at the end of this Borexino experiment, they try to identify this, the solar neutrino, the directions of this solar neutrino. Neutron what happen, it can also get the direction of this, mainly using the Cherenkov photons. And I will not go to this the light attenuation. When we have the big detector in this Kamiokande and other cases, this is the light attenuation in the pure water. This is this attenuation is very large. But when we use our detectors, there the sea water and other place, this is the attenuation length is about 30 meters. And it is not negligible when we talk about this, our detectors is, let's for example in ice cube, it is this 1 meter cube, 1 kilometer cube. So that means the length is 1 kilometer detectors. Their attenuation length is 30 to 40 meter. That means the light is produced, it will not go to the whole detector. Okay, this is another thing. I will not talk to you much. Srubabati, how much time I should take? I started I think about 10:30? 10:20. Okay, so I know 10 to 15 minutes. So the solid state detectors, these detectors, this is the, in the preschool I talked to it. Basically you have to go the reverse bias mode, where we have that insulating regions where there is no free carriers. And when the charged particle pass through, it produces the electron hole pairs. This, with this external electric field, it will produce and it will collect the signals. And what is the depletion voltage? It depends on this, what is the free carriers using this, and this is the width of the depletion regions, it comes to this formula. And the charged particle typically created to into the 30K electron hole in the 300 micron silicon detector at this point. Okay. Now this, why I showed this, I think I will not talk about the silicon detector in the next 2-3 days, but again I try to tell that this is this concept when you see in the textbook. It says that electron hole pair is produced, and this electron is coming here, hole coming here, electron coming, propagate this, here we put the ammeter, we see the current. This concept is completely wrong. Do you know what is the drift velocity of this electron in copper? That's the conventional conductor we used all the electronic circuit. We do not use the gold or silver, even though those are the more conductive. Do you know anybody? I showed here a little bit. What is the drift velocity of the electron in copper? Which gives you the signal? It is a millimeter per second. I think millimeter or 10 to the power minus 10 to the power. This is the millimeter per second. Our copper wire, we say that this is the copper wire, it is the few centimeters where you connected. So this we say that the signals, if the electron moves in these wires, the signal it will take a tenth of second to get your signals. But in the silicon sensors, we say that we see the signals in 3 to 10 nanosecond time. And 3 to 10 nanosecond time is nothing but this, when this electron is drifted within the end, in this external field electron hole drift velocity, and that in 300 microns, that gives me my signal, induction signal. Okay? So just these two numbers you see, this copper, if it is the millimeter per second, we cannot see the signal through this way. Okay? So that's the word, again I am repeating, all signal in particle detector are due to the induction of moving charge. This is in the gas detectors, all the detectors. Once charge arrives at the electrode, the signals are over. So this is the other way I try to talk about. If you see this PN junction, that's the way. Let's say this is the depression region. I put this applied voltage. Now this is the length. What is my electric field we'll see? This is the, as a function, what is the electric field we'll see? The electric field, if we see, this electric field will be like this. Only these regions we have an electric field. This looks like a conductor. There is no electric field in these regions. And then when there is no electric field, then how electron will move? Okay, this configuration, this is a completely conductors. This is my insulator region. All the electric field in these regions. This conductor, the electric field is 0. That's the definition we put. So there is no motion of the charged particle in that regions. Okay, so this is the, I do not know why the textbook does not tell this, and all this, across my life, whenever I come to the student, all the students give this wrong answer. That's why every lecture I try to hammer again and again few times this concept. Okay, so now other devices is uses. This is mainly for the low energy signals. When the neutrino interacts, it's absorbed this energy, and when it absorbs the energy, this is the inside the temperature is increased. Now if we have a sensors where the resistivity is very much dependent on the temperature, this is called a transition S sensors, and then we get then this transition S sensor means when the slight variation temperature slightly changes, the resistivity go for superconductor to the, let's for example, my insulator. So resistivity increases very much, so that gives us the signals. And that is the thermal sensors. And in the fourth lecture, when I talk about this neutronless double beta decay, that time I talk about these bolometers with the scintillator, all these properties. Okay, so now other thing, the Cherenkov light, this I also discussed. Basically, when the charged particle pass through the medium, where the velocity of the charged particle is more than the velocity of light in that medium, not in vacuum. Nothing can be go more than velocity of light in vacuum. So then this is the kind of when the charged particle is here, because of the charged particle it produces the electromagnetic wave, and charged particle when it comes here and here, and in these configurations, this wave what is produced, it comes like this. When the charged particle here, this wave can like this. When the charged particle here, this is the wave just started. This plane, there in that plane, all the particles are polarized in the same directions. And then again, this is electromagnetic wave. If we interpreted this, that gives the Cherenkov photons. And as I mentioned, this is the Jackson's books is the best to get all these derivations. And this is the number of particles what has produced Cherenkov photon. This number is very, very small. This number is this roughly 100 per centimeter ice and waters when beta is equal to 1. In this air, atmospheric Cherenkov we use, that's very, very number is less, 0.15 per centimeters. And so that's another thing. In the textbook wise, I say that student, you just say that I see this wavelength of these photons and we converted the energy. So this is the simple example. If you just keep this mind, handy way, this number is not exactly right. If you know the wavelength of these photons, what is the energy, you can calculate through this way. Energy in EV is the 1, 2, 3, 4 by lambda in nanometers. So let's say the UV photon 400 nanometers, its energy is roughly this 400, so roughly 3 electron volt. This number is I think 1229 or something, but this is the simple way to remember. So that means if you say that this many photons are produced, that means energy loss due to the Cherenkov photons is much smaller than the ionization energy loss. Here less than a keV energy loss happen, where the ionization energy loss is happening about the MeV range. And this is the detectors we used, Cherenkov lights. Okay. This is the reactor core. If you see the reactor core, we see Cherenkov. Detectors was used mainly a radiator where the photon is produced and the photon is collected at a certain distance and calculate the angle. From the angle, you can calculate this, your velocity and others. And In neutrino physics context, this is the way you use. Neutrino interact, produce the charged particle. This example for this Kamiokande, it produces the Cherenkov photon and the photomultiplier will see the signals. And this is the signals it can produce the charged particle. Charged particle can be this muon or the electrons. When muon produce the signals, muon does not go to the whole path length, maybe muon from here to here, it will lose all the energy through this ionization energy loss. This is the detectors go to the few meters, so this will lose it. So we will have the Cherenkov photon, this is the within this area. But for the electron also produce the Cherenkov photons, but the Cherenkov photons will not be as sharp as that. This is the kind of in pictures. When the electron go to the medium, electron will produce what called electromagnetic showers, electron and gamma and electron, many electrons. So the direction is diffuse. So for this muon detections, this is the outer edge is clearly visible. Maximum it can go, this is this way. But for the electromagnetic showers, this is the diffuse. This is the electron what they produce, they have the different angle, so the Cherenkov photon can go out of this angle. So this basic principle is used for the Kamiokande experiment to identify this electron and mu, and then corresponding electron nu and tau. Now,
Gobinda, should we start this later?
Fine.
Because it's already 11:20.
Okay. Okay. That's fine. Yeah. So let me, whatever the way I say that this is the full lecture, how much I can continue. I will start from here. And
it's a reactor thing. So
no, not the reactors. No. Okay.
I am saying that.
Yeah, I'll stop here. So basically, until now I talked about the different source and different instrument. Now I am trying to combine these two. This is the energy of these electrons, and this is my neutrino. This is the energy will produce. Now I will use the detector. So I will start from the next. Okay, next lecture.
We will take We will take one or two questions, but we are a little bit running late, so you can also discuss over.
I am here today, tomorrow, whole day, anytime.
Yeah. Questions? Yes, please.
Sir, that I understand that ultimate signal is the photons that we are detecting in our detector, but you have mentioned that those gamma radiation are not different from the visible gamma photons.
Yeah.
So that I didn't understand how they are different.
So this is when the positron emission happen. Where I put it? This is this positron annihilation. E plus coming to in the material, it has the electron. So it will E plus emits the annihilate produce the two photons. This photon energy is 511 keV. Energy, that's I mentioned explicitly in this next point. This produced gamma is MeV order. And when this is produced, this E plus E minus gamma, it go to the Compton scattering. This energy will be the 511, maybe the let's say 300 EV, 300 keV. When it go to the medium, it loses the energy, produce these scintillation photons. That scintillation photons is of the order of few EV.
Or
our signal, observed signal is these photons. But we are from that photon, we will retrace back. This is my initial photon. Okay. What happened, we do not know. In this experiment, we will see these photomultipliers, we will see this equivalent number of photoelectrons in the photomultiplier. And photomultiplier, what is the number of photoelectrons you see, that is the EV energy range. So now in this experiment, that's the part of the calibration I just mentioned, I will talk. If I see these photomultipliers, I see the 100 photoelectrons, then I know this 100 photoelectrons coming from that, what is the initial energy of the photon. But my signal as observing is a visible 2 to 3 EV photons.
Anyone else?
On the right side.
Hello, sir.
Yeah.
Why the quantum efficiency of the PMT is always less, like around 30 to 40%?
Where it is? Where my photomultiplier? Okay, so the quantum efficiency of the photometer is the glass window you have to keep. We have to keep, and this is the vacuum. We have to put a glass window where the photon falling on it. This glass window itself absorb that is the probability that photon will absorb within the window. Okay, so the photon, though that I did not talk, this is the photon attenuations. It depends on this, how much is the absorption coefficient of the photon in the different material, depends on the wavelengths. Okay, so some of the photons will absorb within this window, and we put the photocathode material. This is some material, photon pass through the medium. It does not mean this always the photon will interact with the photocathode material. This absorption coefficient is there. So each material photon may absorb. So this probability of the absorption of the photon in the photocathode material, that we try to maximize. But as you know, the photon interactions, any material, any medium when photon pass through, this is the distance x and the intensity goes like this. I is equal to I0 e to the power minus x by lambda. Lambda is the attenuation length of the photon in the medium. So if I put, let for example, this is our something like, say, assume, let's say this is my glass window and this is my photocathode window. This is the different material. You have a different material where the attenuation is more. So the lots of the photon will absorb in the glass. Only the small fraction will absorb in the photocathode material and remaining will pass through. So only which are this attenuation in this range, that this only my signal we see, that many photons we see, but remaining we do not see. And okay, in that word I say that when this energy of the photon is increased, when the energy of the photon is increased, my absorption coefficient is increased. So that's why when energy is more, this is the more photon absorbed in the glass. This quantum efficiency decreases. And when the energy is reduced, then the absorption factors in this photocathode also reduce. So that's why this again this quantum efficiency is reduced. So this is the optimum where I have a maximum here. When the wavelength is more or less, my absorption in this photocathode material will reduce.
Okay, so I think let us break for tea and try to come back by 11:45.
Okay, if you want to see these things, sometimes I keep it here. You can see, you may ask this question, the scintillators. These are two different kind of scintillators and two different kind of fibers I put it here.